Hi there. I had the chance to work on the garage door project a little bit over the break, and I wanted to take you through what I experienced and what I learned with respect to uh, getting hardware SPI working with the Adafruit ST7565. So it took me a little while to do this, but primarily because, as you can see here, I've relayed out the board a little bit, and I added some additional, or an additional component. Down here I have a I2C port expander, and I added that in to read the garage door sensors and to read the buttons, and then to control the relays that I'll be using to drive the lights. And so that meant that I needed to lay out the board a little differently so that I had space for the display and so on. But fundamentally, it's the same experience, the same electrical sort of layout as I had previously. I have my Intel Galileo Gen2 over here running Windows, coming in, talking to the 4050 being used as a level shifter. That's bringing it down to 3.3 volts. That I'm now supplying through a little LM317 set up to create a 3.3 volt rail for me, so I can bring that off that rather than taking the 3.3 off the Galileo, and then driving the display down here. So as you may remember, or may have seen previously, I had a video which showed utilizing the ST7565 and the Adafruit libraries with software SPI. And that software SPI wasn't particularly performant. If you look up, I'll have the video and display there. You can see it very slowly painting the screen. So what I started doing and how I got to where I am now was I got the Adafruit libraries working on the Intel Galileo in software SPI, and I wasn't really happy with the perf, and I wanted to get a better performance experience from it. So I went and started looking at this U8Glib, or the Universal Graphics Library for 8-bit embedded systems. And I thought, well, this is a richer library. It has a wealth of support for hardware. It does hardware, software SPI. So this would be great. I'll grab this, bring this over, and hope that this was going to be a much more performant experience. So I started utilizing this library to get it up and running under software, and I discovered that, well, in software SPI, I still have the same basic performance problems. So what I needed to do was to go through and start looking at how I could make the library use hardware SPI, and it really actually wasn't that hard. But the U8Glib stuff is fairly complex in how it has many files and calls back and forwards and so on. So I wanted to start by simply turning the Adafruit libraries into hardware SPI. So if we go over here and have a look at my VSO account, we can have a look at the ST7565 libraries. This is just the pull straight down from Adafruit, from the Adafruit GitHub. And you can see that I did some work initially, and I've already gone through a lot of the work that had to be done here on making the ST7565 libraries work with Windows and the Visual C++ compiler. And you see that I added some defines to take into account things that didn't exist in our implementation in the compiler. One of the things you'll notice is the difference between this video and the one previously. When you look at it, is there are some macros in here that in the 1.00 version of our new wiring API that we've just released, we defined those macros, so I don't need to define them again. And in terms of the actual CPP file, I needed to just get the headers to work correctly with Windows and Visual C++, and I needed to tell it that it was an extern. And similarly on the font file. It was that similar sort of header things to make sure the right includes are added compared to the non-Windows stuff. So that was really all I needed to do to get it to work with Visual Studio and Windows. And moving this over to Hardware SPI was actually pretty easy. What I needed to do to make it work was just include the SPI header library, and then I just changed the SPI write call that was in the CPP file to, instead of using a shift out and pushing it out a bit at a time, I'll just use the SPI transfer function. Now, next thing that I needed to do was to go in and tell it, okay, you know, I've got to set up the SPI class. And so I needed to put an SPI begin somewhere. And I just did that in the main CPP file. You could go through and look at the Adafruit libraries and work out where the class is being initted and do the SPI begin there. Because I was just trying to get a handle on what I needed to do, I didn't bother doing that here. But I started running it, and great, it started rendering very well. The performance was great. You can see it. I'll include the video just in a window so you can see the perf difference. And it was really driving that hardware quite well. Now, that was all I could do at that time. So I shut everything down and I came back. And when I powered back on and went to continue development, it wouldn't run anymore. It would run, but it wouldn't print anything. And so I was wondering, you know, what have I done? Has something changed in the hardware? Has a chip failed? And so I started probing around with my Rigol. And what I discovered when I was looking at the different waveforms was this. On the left here, you can see the 5-volt waveform coming out with an SPI clock of 2 megahertz. And you can see that I've got a nice, I've got a recognizable waveform for the clock. When I looked at the 3.3 volt output, I saw that that turned that square wave into really, you know, a sawtooth wave. And so I was wondering what the hell's going on, and I went looking at the hardware. I tried some different channels on the 4050, and eventually, you know, I did what I probably should have done originally, which is to crack open the data sheet and look at the rise and fall times of the 4050. And at 3.3 volts, it does have a greater than typical 120 nanosecond rise time on it. So what was happening was in the right-hand column, when I was running it at 4 megahertz, even though the square wave for 5 volts still gave me a recognizable square wave with full voltage on it, the 3.3 waveform, because of that rise time limitation, didn't get up to the proper voltage before it dropped off, and so it simply wasn't working with the ST7565. So I need to do either replace the 4050 or look at exactly what's going on in how I have it wired up to see if there's any stray capacitance in there, because the rise time is a base plus a certain value per picofarad. But what it really meant is that I just had to slow down the clock. And so in this particular case here, I slowed it down with SPI clock div 16. And this enabled now the waveforms to be correct and for me to be able to drive the display. With this working, I thought, well, great, now I can get started on looking at the U8Glib stuff. And so I grabbed the U8Glib stuff and I started working on the hardware implementation. So let's ignore the main file for the moment, because that was primarily where I took one of the Hello World, sort of the example applications that they ship as part of the U8Glib, and put that in there, put that in main. Most of the work was done here inside these utility and the U8Glib library itself to get this stuff to go. So the first thing that I had to do was to come in and define my own, or create my own definition for the Intel Galileo. What it does is, as you go through and use these different different devices, it reads a bunch of predefined definitions and goes, okay, if this is the device you're using, do these things. And one of the things that it does is starts to hook up these tags with these individual functions that exist inside the various files. So I had to go fix that, and then I actually had to go into the hardware SPI file and create my own implementation of the hardware SPI. So I grabbed one of the existing implementations and just went through and started looking at it and said, okay, well, I can copy this and use most of this stuff. Most of it is appropriate the way it does the SPI out. I'm just going to turn that into an SPI transfer call, and then in the message start, message stop, I'll do the SPI begin, I'll do the SPI end. This will set things up. And so now I'm all good to go. And I was able to compile this and try to get it to run. Well, one of the things that I discovered when I ran this was that it threw an error back at me. I got an exception. And the exception that I was getting back related to the use of the pins. In our implementation of the SPI class, when you say I'm using the SPI class, we will lock for SPI use pins 10 through to 13. So you get clock, MOSI, MISO, and slave select. And typically, the U8Glib guys will use slave select or chip select, and you'll give it a pin value. And in fact, in this first one here, you can see in the software version that I'm telling it that it's going to be pin 10. Well, actually, I'm not here because I fixed this code. But I was telling it that it was going to be pin 10. And that, of course, was already locked. And in the U8Glib init code, it basically goes through for the Arduino and sets all those pins to be outputs appropriately and so on. So rather than doing that, rather than going in and looking to see how it set all those things, what I did instead was just simply rewired the circuit a little bit so that I don't use one of the SPI. I don't use chip select and get it knitted as part of the SPI pins, but I can use it for A0 because of the way the code's written. So I went off, did that, flipped that around, and got the code effectively working, and now it would write to my device. Now, when it started writing, what I noticed was that the 7565 has 8 pages that it will write to cover the memory and the display. And I was only ever writing the first page. It would never write anything more. And this is where one of those reasonably priced logic USB-based logic analyzers, and I'm going to get the name wrong, like the Saleae Logic analyzer can help you out. What I was able to do was to take that logic analyzer, plug it onto the board, and look at the initial 10 seconds or so of the SPI bus. Now, I had software SPI working, so I knew that it was writing the correct information, and the hardware SPI should be identical to that. So I was able to capture the 2 different runs and compare the items together. And I noticed that what I was not doing was not issuing an incremented page count. And this enabled me to go in and inside Visual Studio set a conditional breakpoint for when the page count was incremented and run the software version, break on the page count being incremented, then look back at the stack to find out what was going on. And what this enabled me to do was to find out that the bit of code that I actually copied from one item to another was included a little flaw in it. Let's go here, and this will should show it a little bit better. it had a return in the incorrect location. So I was returning an incorrect value that caused the page processing basically to stop. Once I fixed that up, everything started working really well. And so if I go into Visual Studio, what we can see now is with the U8Glib, I can specify either hardware or software SPI by simply utilizing the right object and specifying the appropriate constructor. And so in this case, you go and spec all of the things you're going to be using, and that tells it to use the software one. In the hardware one, you just give it the CSA0 reset being optional. And then what I have here is basically the frame per second test example that they had, and this enables you to go through it, draws a bunch of stuff on the screen, and then captures that. So if we run this and go and have a look at the device, what you'll see is the device will clear, and now that screen paints very well. If we just move that over a bit, make it a little bit more visible to the camera, and you can see that I'm getting a logo test now of 17 odd frames per second. To put this in comparison to the software version of this, when I run the software, you actually get dramatically poorer performance on this. So let me show you what the difference between the two is. Now I'll use the 2x for software SPI, which is basically supposed to be faster because it pushes 2 pages at a time. So let's run that. And if you look again now, you can see it go back to that very software, very slow driven model of painting a page, and you can see that I'm getting like a 0.2 frame per second. So the easy move from the software to hardware SPI not only improved the performance of the application and performance of the hardware and that, but it also helped me decrease the number of pins that I'd be using on the Galileo. Now the next thing that I'm going to be working on is there's a library called, I think, M2TKlib, which basically is a menuing system, supports touch displays as well, but it's an open source menuing system that enables you to use U8Glib as the rendering engine. And so I was able to bring that up and have that, and here you can see a very simple example. It's just going to draw hello world, and it uses all the same existing code that I had to use to make the U8Glib works. Basically, you tell it what your rendering engine is going to be. You create a version of your hardware or of your display device, and if we run this, what you'll be able to see is just across the bottom of the display, you should just see hello world come up. And now I can go in and start to look at using a rich menuing system as part of the display for my garage door project. So in the next video, hopefully what I'll be able to do is go through utilizing the I2C port expander to work with the buttons and show you that working with the menuing system. I wanted to show you one last thing actually before I go, and that's I've placed both these modified libraries just in their current state. They haven't been religiously cleaned up. If you were going to go use this, you could go in and make go in and update how where SPI begin is called and so on. But you can go up to GitHub tgoodhue ST7565 and you can grab that this code and see how the changes that I made, and just do a diff and compare it to the existing U8Glib and the existing Adafruit libraries to get a handle on how to make hardware SPI work with an Intel Galileo Gen2 and a Windows image.